Computational fluid dynamics (CFD) is a branch of fluid mechanics that uses numerical analysis and data structure to analyze and solve problems that involve fluid flows. Computers are used to perform the calculation required to simulate the free stream flow of the fluid and the interaction of the fluid, liquids, and gases with surface defined by boundary conditions. CFD simulation provides comprehensive data on the flow field, including velocity distributions, pressure gradients, temperature profile, and other relevant parameters. Basically, the experiment was conducted to determine the relationship between the boundary layer thickness and the fluid particle velocity. The experiment can see how boundary layer and CFD interact with each other. For this experiment, ANSYS software has been used to generate the CFD file, including for the profile plot. Theory of CFD. CFD is based on numerical analysis and fluid mechanics concept. CFD is a powerful tool for studying and simulating fluid flow behavior by solving governing equations using computational methods. The Navier-Stokes equations are the fundamental principle of CFD theory, which explain the conservation of mass, momentum, and energy in fluid flow. This is formula for continuity equation and Navier-Stokes equation. Discretization techniques are used in CFD to convert continuous equations into a discrete form that may be solved numerically. Boundary conditions define fluid interaction and computational domain values, ensuring a realistic representation of flow by specifying variables at the boundary. In addition, Reynolds number equation also will be used to determine whether the fluid flow is laminar, transitional, and tubular flow. This is an equation for the Reynolds number. Objective of the project: to demonstrate the fundamental of CFD simulation using NSYS software, then to determine the relationship between the boundary layer thickness and the fluid particle velocity. Lastly, to investigate on how boundary layer and CFD interact with each other by using NSYS software.
Next, we look at the methodology to run this experiment by using NC software that have been downloaded, and run the NC software at the laptop. Wait until the tab software appears on the screen. When the NC software appears, find the fluid flow fluent at the left side of the tab, and then double-click. A small new tab will appear consisting of geometry, mesh, setup, solution, and result for the experiment. Right-click the geometry part and then find New Design Modeler Geometry option. Wait until the NC's Design Modeler tab appear. After that, click the Z-axis at the right bottom of the tab to make the orientation from X and Y axis. Click XY plane and go to Sketching and find Settings. Turn on the grid in 2D and Snapbots. Then, change the major grid spacing to 0.1 meter. And minor step per measure to 10 meter. Zoom in the plane until we see the grid. Next, find Draw option and click Rectangle. Draw a rectangle without the dimension. Find Dimension and choose General and make a dimension of the length as known as H2 as the width as known as V1. Since we are from group C, the dimension of V1 and H2 and have been changed into 1 meter and 0.5 meter. Next, find Concept at the top of the tab and then choose Surfaces from Sketches. Double-click the XY plane and then click Sketch 1 and click Apply. After that, click Generate. After done, save the project to the desktop and then name the file as Group C S9K1. Then, close the Design Modeler tab and next double-click the mesh and wait until the meshing tab appears. After that, Click again the Z axis to make the orientation from XY plane. Click mesh and then generate mesh. Next, right click the mesh and then insert face meshing. Click the face part and then click apply for the geometry. Click generate mesh. Click again the mesh and the insert sizing. Find edges and then click the top edges of the rectangle and then click apply. After that, click the bottom edges and then click the plus icon. Change the type from the element size to number of division. Set the number of division to 50 of the capture curvature to no and then change the behavior to hard. Then click generate mesh. After that, do the sizing for the left edge. Change the number of division to 60 of the capture curvature to hard. Choose the bias type by clicking the first bias type. Next, define the bias factor to 70 and then generate mesh. Insert the last sizing for the right edge. The same steps need to be repeated until 70 of bias factor have been defined. Click reverse bias and then click the right edge, then click apply. Then generate mesh for the right edge. After that, right click the face for the rectangle and then find the create name selection. Name the face into airflow, left edge to inlet, right edge to outlet, bottom edge to plate, and the top edge to far field pressure. Next, check all the mesh and the name selection that have been defined. After that, close the tab. At the small tab, right click the mesh part and then click update. When the mesh has been updated, go to the setup part.
Okay, next we look for the setup. Double click for the setup part on the small tab. When the Fluent Launcher appear, tick the double precision box and then set the solver process to number 2 and then click start. Now we will wait until the Fluent tab appear. It will take a few seconds for the Fluent tab to appear. We will wait until then. Now the Fluent tab has appeared. We click OK. After that, click check to investigate whether there are any error. If not, for this experiment, for this part all the options need to be double click. Now we go to the model at the setup and then we change the viscose to lamina. We choose lamina and then we click OK. Then click on the material part. Double click the air under the fluid part and then change the air density to 1 and the viscosity to 1 times 10 to the power positive 20. We choose air and we change the density to 1 and the viscosity to 1 times 10 to the power of positive 20. And then we click change or create and close the tab. After that, we go to the boundary condition and then change the far field pressure type to symmetry and then apply it. Click symmetry and apply. Next, we double click inlet and set the velocity magnitude to 1.5 meter per second since we are from group C. And click apply. After that, we will go to the method and then change the scheme from couple to simple. Now go to the monitor and then double click the residual part. Add 3 more 0 after the decimal point for all the residual which are continuity, x velocity and y velocity. After finish add 3 more 0, we click OK. Now we will go to the initialization. We will change the initialization method to standard initialization from hybrid to standard. And then we change the x velocity to 1.5 meter per second and we set in compute from inlet. After that, we click initialize. After that, go to the run calculation and then change the number of iteration to 1000. Next, we click calculate. The scale residual graph will be generated with the x-axis represented the number of iteration and the y-axis represent the residual of each equation that have been solved. Now, we will wait until the graph have been completely generated. Okay, after the graph completely generated, we click OK. Next, we will save the project and then close the tab. Click File, Save Project and close the tab. And then we go to the result part on the small tab again. Double click it. Okay, after double click it, CFD when the CFD post tab has been appear, we will set the orientation into XY plane. Change the orientation into XY plane. Okay. Find contour at the top of the tab and then change the location into symmetry 2 and the variable into velocity. Symmetry 2 and then variable to velocity. And then set the number of contour into 50 and then click apply. Now the velocity contour will appear on the tab. Then insert line for the contour. At the geometry part, set the location for the point 1 and point 2. Set the x coordinate from point 1 to 0.5. Next, set the x and y coordination for point 2 to 0.5 and 1. And then we change the sample to 100 and then click apply. Insert chart for this contour. Go to the data series and then set the location to line 1. Go to x-axis and then change the variable to velocity u. Next, go to y-axis and then change the variable to y. After that, click apply. The graph will appear on the tab consists of head, which is y versus flow velocity, which is velocity u that represent the profile plot for this laminar flow. After that, save the project and close the tab. After done, double click again the fluid flow fluid at the left side of the main tab to continue the experiment for 2 meter per second velocity of the airflow. All the steps to run this experiment will be repeated for the next velocity. All the value for the steps are same accept the airflow velocity need to be changed into 2 meter per second.
Okay, next, let we look for the results and discussion for this experiment or CFD simulation. Okay, this figure shows the flow patterns of the laminar flow, where the laminar flows occur at a low Reynolds number, in which any induced perturbation are damped out due to relatively strong viscous force. Okay, this figure shows the time history of local velocity variations for laminar flows respectively. This pattern can be obtained from hot wire anemometer measurements or CFD simulation. For the pipe flow case, laminar flows have nearly constant velocity fluctuation patterns, but for a cylinder in cross flow, laminar flows produce a sine wave velocity patterns at a downstream location of the cylinder. Okay, these figures show the profile plot of the laminar flow that have been generated from the CFD simulation. The left figure shows the profile plot of the laminar flow with 1.5 meter per second for the velocity, while the right figure shows the profile plot of the laminar flow with 2 meter per second for the velocity. Okay, since we are from the group C, the maximum velocity for 1.5 and 2 meter per second airflow remains constant as Y value are increased. This behavior points to a laminar boundary layer in which the flow stays connected to the surface for a greater amount of the time and the velocity gradient is comparatively smooth. Okay, next we look for the conclusion for this experiment. When the surface roughness and the fluid viscosity are increased, the boundary layer thickness will increase, but the velocity of the fluid particles will decrease. Okay, generally, turbulent flow boundary layer is thicker than a laminar flow due to their Reynolds number values, which is the laminar flow has the smaller values for the Reynolds number compared to the turbulent flow. Thus, all the objectives have been achieved. Okay, that's all from us. Thank you.